So 6.5a is all about the law of sines. Now, in this section, we only have one particular goal, which is basically the overarching theme of the entire Unit 6, and that is to solve any triangle. Now, in the past, I think it was 6.2 and 6.3, we solved right triangles, specifically right triangles. Today, we're going to be able to solve any triangle I give you, be it right or not, using trigonometry. Now, that goal seems pretty lofty and pretty contradictory. If trig, that is to say sine, cosine, and tangent, if they can only live in right triangles, how are we supposed to use them in a non-right triangle situation, since, by definition, sine, cosine, tangents are ratios of side lengths of a right triangle? Well, the idea behind this concept is very simple. It all goes back to the fact that, since we learn in geometry, in any non-right triangle, we can always drop an altitude to create right triangles. As a matter of fact, we used this idea back in 6.3b when we developed the formula for the formula of developed the formula for the area of any triangle. So recall, right, the area of any triangle, if you know two sides and their included angle. Now, to go back even further and remember our geometry days, I believe in your geometry class, your teacher probably called this the side angle side, or SAS situation, right? So for any triangle, and I'm going to do my best to try to make it not look like a right triangle, if you have two side lengths and the angle in between them, the area is always 1/2 times the product of the sides times the sine of their angle. So that's the formula that we developed back in 6.3b. Now, when we develop this, what we choose as theta is completely arbitrary. As long as you have the angle within a triangle and you have its adjacent sides, you should be able to find the area of, well, any triangle that I give you. So let's see what type of formulas we get when we take a look at the other angles. So consider an arbitrary triangle, ABC. Arbitrary means there's nothing special about it. It's not a special situation. It's a general case, just a random triangle ABC. Now, I'm going to, my drawing abilities isn't that great, so it may not look the same, but the idea is that these guys should be congruent, right? So let's say we had triangles A, B, C. Actually, I'm on a computer. Let's see if I can copy and paste. Can I copy? I think this is copy. Paste. Perfect. Oops. And paste. Perfect. Blah. Sorry for the technical difficulties, but I want them to fit all in the same page. There we go. So let's just go ahead and delete these two here. Delete. Okay. So here, you guys saw me just I made a generic triangle. Oh man, I overlapped them. How such an idiot. Sorry, it's taking a while. I guess I should have prepared this ahead of time. Paste. There we go. Third time's the charm. Paste. There we go. Okay. So here we have three triangles, and since I just copy and paste them, they are congruent. They have the same side lengths, the same angles, the same area. So let's calculate the areas of these three triangles here. So if I were to focus on this side here, or excuse me, this angle there, angle A, I need to use his adjacent sides. So this is side C, this is side B, right? So I hope everyone can agree that the area of triangle number one, I'll label them triangle number one, triangle number two, triangle number three. The area of triangle number one, according to the formula, is 1/2 BC sine A. Well, what's the area of the triangle number two? So suppose I focused on this angle here, right? Well, I need his adjacent sides. This is side A and this is side C. So according to the formula, the area of triangle number two should be 1/2 AC sine B. And since these two triangles are congruent, I literally just copied and pasted them. They should have the same area. So what is the area of triangle 3 if I were to focus on this angle? Well, I need his adjacent sides. So this is side B and side A. And according to the formula, it's 1/2 AB sine C. And again, since these are all three congruent triangles, all these areas should equal to each other. So the relationship that we wrote down here should be 100% valid because they represent the same area. We just took a look at a different angle. That's why the formulas look all different. Well, because this is a valid equation, I can do whatever I want to with him. I can manipulate him as long as I, follow the rules of algebra, balance the equation. Well, notice how they both have a 1/2 in here. So let's get rid of the 1/2 by multiplying everything by 2 or dividing by 1/2. And this gives us BC sine A equals AC sine B equals AB sine C, right? And just in case you're looking back at your notes, all we did was multiply by 2. And then at this point here, what I want to do is let's divide everything by all the side lengths. So we're going to divide everything by ABC. And again, this is completely legal to do because, well, you're balancing the equation. Notice in the first fraction, the BC's will cancel out, and it'll give us sine A over little a. In the middle here, it'll give us sine B over little b because the AC cancels out. And on the third side here, the AB will cancel out, giving us sine C over little c. Now, this is a sort of an interesting relationship here. We got sine A matched with his letter A, sine B matched with his letter B, sine C matched up with his letter C there. This relationship here is what is known as the law of sines. And notice we started with an arbitrary triangle. Now, it wasn't a special right triangle. I didn't say, oh, this works for obtuse. It's for any triangle. So that is the law of sines. It turns out, it's sort of amazing how math works this way, that these ratios, these proportions are preserved in any triangle. For any triangle, ABC, we have sine of A over little a equaling sine of B over little b equals sine of C over little c. Sometimes, though, we may not want the angles in the numerator. We want the side lengths in the denominator. So it's completely valid to flip these fractions as long as you're consistent. You can have little a over sine A, little b over sine B equals little c over sine C. So that's what you typically find when you Google law of sines or read math textbooks, law of sines. I sort of like to understand it verbally in written form because the concept is more important than just blindly memorizing formulas. So what? What does this equation mean? What does this relationship or formula mean? In layman's terms, in any triangle, the ratio of the sine of an angle to its opposite side is constant or preserved. That is to say, in any triangle, you can take the sine of any angle, divide it by his opposite side, or vice versa. You can take the side first and divide it by the sine of the angle, and that should equal, that should be a constant number that should be the same if you took any other angle. This is very useful for us because it allows us to use trig, specifically sine. It allows us to use sine in a non-right triangle situation because we know that this relationship, this proportion, this ratio is true. So my little tip or hint, we typically use law of sines if we have an angle and its opposite side. If you have an angle opposite side pair, that is usually the dead trigger, the giveaway that says, you know what, this is a law of sines problem, right? So there are a lot of little hints or triggers that tells you what to do in a math problem. If I'm solving a triangle problem and they give me a right triangle, that's your normal trig, SOHCAHTOA. If they give me a triangle problem and I have an angle opposite side pair, 9 out of 10 times it's probably going to be a law of sines problem. Let's take a look at a couple of examples here. So suppose I ask you to solve the triangle. And I gave you this looking triangle here. Let's call this ABC. And I tell you angle A is 80 degrees. Side B is 3.4. And side A is 6.5. And that's all the information I give you. Right. So let's go ahead and dive into this. Recall what it means to solve a triangle. To solve a triangle means to find all the missing pieces. So whatever's not labeled, I hope it's very obvious to see that angle C is not labeled, angle B is not labeled, and side C is not labeled. So those are the three pieces that we need to solve for. It's not a right triangle, so I can't use regular SOHCAHTOA. This seems like I'm stuck. So this is what you should notice. We should notice 80 degrees and 6.5 are angle opposite side pair, or is, proper grammar, is an angle opposite side pair, right? So the moment you have an angle opposite side pair, that means law of sines, right? So look at the information you're given. So here's our angle opposite side pair, and the only other information I'm given is 3.4. Remember, law of sines can only be used in angle opposite side pair. So for this particular problem, I can't really have free choice in what to solve for. I am forced to solve for one particular piece of information, namely, in this particular instance, we are forced to start off solving for angle B because, you know, that's the only numerical information we have. So let's set up the law of sines. Now, there's no right or wrong way to do this. I typically like to put the thing that I'm solving for in the numerator. So since I'm solving for angle B, I'll start off with sine B. So then in the denominator would be the side length. Remember, it's always the opposite side, so 3.4. So then you set it equal to another angle opposite side pair. Well, the only one we have is this guy, so set it up. Sine of 80 over his opposite side. Lo and behold, it gives you a proportional equation that we can then solve, right? So solving for B, here's angle B there. I got to get rid of the 3.4, so we're going to multiply both sides by 3.4. Oops, 6.5. And then to get rid of the sine, I have to take the inverse sine of both sides. So B equals sine inverse of 3.4 sine of 80 degrees over 6.5. That looks like an ugly mess, but then, you know, we have calculators. So making sure our calculators are in degree mode, pop that guy into a calculator, we're going to get about 31 degrees. In hindsight, I guess I should have color coded this. So this should be all of this color here. highlight it for you. There we go. Now, once you have angle B, notice you have 2 out of the 3 sides of a triangle. We have this guy and we have this guy. So that should be very easy to solve for angle C. So for angle C, we should know that 80 degrees plus angle B plus angle C should be 180. That's the geometrical idea of a triangle. The sum of the interior angles should equal 180 degrees. So that means angle C should be 180 minus 80 minus angle B. But we just solved for angle B. So that's 180 minus 80 minus 31 abouts. So that gives us angle C to be 69 degrees. And notice what happens here. Once we figure out angle C, we can use the law of sines because now the angle opposite side pair is valid. So to solve for side C, notice since I'm solving for side C, I'm going to put side C on top first over the sine of its opposite angle, which we said was about 69 degrees, and set it equal to another pair. Now here's my second tip or hint to you. I always use given information as much as possible. Technically, I could use the law of sines with 3.4 inside and angle B, but because angle B was a calculated value, there's some rounding errors. I'm going to use these values here because that's what was actually given to us. We didn't estimate, we didn't round, it was given. So to solve for side C, I'm going to use angle A and side A information. Now, since I declared that the side length should go in the numerator, I'm going to actually put the 6.5 on top and then the sine of the angle 80 degrees on the bottom. So then this should be a one-step problem. To solve for C, you multiply both sides by sine of 69. C equals 6.5, sine of 69 degrees, all over sine of 80 degrees, and then the rest is just calculator work. So C is approximately 6.2. So there we have it. We solved a triangle. We found all the missing pieces. And here's the cool thing. It wasn't a right triangle, yet we were still able to use trig, to use sines. And that is the power of trigonometry. It allows us to easily, I don't think this was difficult, it allows us to easily solve a triangle when we don't have all the information. And believe it or not, there are a lot of things in this universe that is shaped as a triangle. So this is very useful. How useful? Well, let's do a word problem, an example. You know, we always have to do word problems. Let's say I want to measure distances, right? That are impractical to measure, say distances to satellites. Suppose a satellite orbiting Earth passes directly overhead at observation stations in Phoenix and in LA. Phoenix and LA are 340 miles apart. And the angle of elevation to the satellite is 60 degrees at Phoenix and 75 degrees at LA. How far is the satellite from LA? Pretty big word problem. Well, anytime it involves word problems and I have no clue what to do, I try to see if I can draw it out, because sometimes the picture makes things easy. And again, you don't have to be an artist, use dots and lines. So I have Phoenix and LA. So here's, I don't know, LA, and here's Phoenix, right? somewhat correct. LA is to the west of Phoenix. And I have a satellite, and it says it's somewhere above them. So here's the satellite. I know the distance between Phoenix and LA is 340 miles because it told me. And it gave me angle of elevation. So I know there's going to be an angle up to the satellite. According to the problem, the angle of elevation from Phoenix is 60 degrees. And from LA is 75 degrees. And it wants us to find the distance between the satellite and LA. So in our picture, it wants us to find X. Now, look at the information that we have. It seems like we are out of luck. I do not have any angle opposite side pairs because this is the only information they explicitly give us. But we have to remember in geometry, if we have 2 out of the 3 angles, we can always solve for the missing angle. So even though it didn't tell us, we actually know what this angle here is, right? That angle there, let's call it angle S. That should be 180 minus the other 2 angles because the sum of the interior angles is 180. And that gives us 45 degrees. So although he didn't explicitly give us, we now have an angle opposite side pair, which means law of sines is unlocked. So use law of sines with the thing that you're trying to solve for. I'm trying to solve for x, which is a part of this pair. So let's set it up. So we're going to do x over sine of 60, because that's his opposite angle, equals the only other information I have. And this is the angle opposite side pair we have. Because I put x in the numerator, that's a distance, that's a side length. I need to put the side length of 340 miles on top and the sine of 45 on the bottom. So there we go. We're done. We're done with the hard part, setting it up. Now all we have to do is solve. To solve for x, you multiply both sides by sine of 60. And just for fun, since 60 and 45 are special angles, we could technically find the exact answer because we should know what sine of 60 is, being a good math student. We know that sine of 60 degrees is rad 3 over 2, and sine of 45 is 1 over rad 2, which, of course, it equals, let's see here, 340 radical 3, right? So if I multiply, take out a calculator, let me find a calculator, I did not prepare one, here we go, 340 radical 3, we get the satellite is approximately 588.9 miles from LA, right? So there you go, short, sweet, and simple. So, doesn't matter if it's a word problem. Doesn't matter if I give you a picture from the get-go. The idea is if it's not a right triangle and you're given an angle opposite side pair, law of sines will take care of all your needs. Go ahead and give that a practice, and good luck.